All right, welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Emma Tegling from Lund University. She's an associate professor there in the Department of Automatic Control and also is a fellow for WASP, the Wallenberg AI Autonomous Systems and Software Program, which is a very cool program. Something about Emma. So I'm very happy to have her. We managed finally to have her. I think that many things happened in between, which is great. So she received a PhD degree in electrical engineering from KTH in 2019, and before Bachelor and Masters of Science in Engineering Physics, always from KTH. Then she was for a while, we were commenting before, a postdoc at MIT at ISS during COVID or COVID happened in between, and also spent some time at Caltech, Johns Hopkins, and UC Santa Barbara. More importantly, Emma's research interests are on the analysis and control of large-scale network systems, focusing particularly on distributed electric power networks and socio-technical networks, which I find super exciting. And today she's going to talk about scalability of distributed control, fragilities, and performance limitations. I think this is a topic that's not often discussed. You know, you oftentimes when seeing these topics, you look at performance, super catchy titles, but fragilities and limitations is something that people don't focus enough about, I think. And therefore, I'm very excited to hear more about it. And feel free to ask questions in the chat and I will monitor. And without further ado, Emma, thanks again for coming. The stage is yours.
Well, thank you, Dale. That was an amazing introduction. Yeah, so it's great to be back at MIT, even if only virtually. So as I said, I've been interested in scalability of distributed control, and I think probably many of you, I don't know you guys in the room, but ideally, of course, I would have loved to have half an hour, meet you over coffee before and chat what you were doing. But basically, showing some kitschy images here. I think many of us are motivated by these emerging large and complex network applications like smart grids with renewable energy integration, smart cities, social technical systems, traffic systems, connected robots, etc., where you have lots and lots of controllers that are distributed or decentralized. And of course, we want and need any controllers designed for such systems to be scalable because the systems are growing larger almost by the minute, and we need to enable a kind of modular and plug and play type design because we can't have a central authority that can retune the controllers and adapt when as new agents join. We need scalability. So of course, in general, such networks are complex and heterogeneous, and there are lots of mechanisms at play, and I'm sure some of you are looking into particular aspects of these problems. But in my case, when I want to zero in on the issue of the scalability of controllers, which is actually complicated enough, I tend to consider a simplified scenario, namely this one, where you imagine that you have designed controllers for subsystems connected in a network, as well as the interaction protocols, basically the means by which the agents can interact with each other. And then you allow the network to grow by adding more and more nodes, typically while still obeying some sort of structural constraints. In my case, I will typically require bounded degrees because communication bandwidth tends to be limited. And then a question of scalability then becomes whether this control design can maintain global performance in the small as well as in the large network. In a power system, you may imagine the small one being a conventional the power network with conventional power generation, where you have tens of nuclear plants or hydro plants, whereas the large system would be a distributed power network with solar panels everywhere and small wind energy plants. And can you use kind of the same control protocols, or do you need something fundamentally different? So of course, there are a variety of scalability issues, and I just made this slide to highlight some of the works that we are addressing in various areas. So one thing that can happen is that you have error amplification. So as the network grows from small to large, you might have unfavorable error amplification. And in vehicle platooning, where you have cars driving behind each other, that's going to be a common example throughout this talk. It's called string instability. So basically the errors propagate along the string. You might have cascading failures. There was recently, I know you probably can't see this picture enough, but there was a blackout in Spain, right, just the other week. So cascading failures is a common topic in power systems. Also can be also an issue of dynamic scalability issue. My PhD thesis focused a lot on a topic of decoherence and disturbance sensitivity, where we could prove that that the simulation in the lower left corner here shows a kind of accordion effect that is unavoidable in large formations subject to relative feedback. And this is something that Bassam Bami and others described in 2012, and we continue to work on in my PhD thesis. And then, of course, a very important problem, which again, I'm sure some people in your group are looking at, is even if you might not have necessarily dynamical issues as a network grows large, you might not be able to do optimal control because it's simply computationally intractable. And you have the curse of dimensionality, famously by Bellman. And here we have some work looking at a new problem class of what we call linear control, so positive systems with linear dynamics that and linear cost functions, which may circumvent some of these dimensionality curses. Not something I'm going to cover today. I just wanted to highlight. So today I want to focus on some issues. I'm going to partly talk about the string instability issue. We're going to revisit that. So the upper left corner, and also another problem which is even more dramatic than some of these, namely something that I call scale fragilities. And I'm going to talk a little bit about how such negative results, so basically describing how limitations can be derived here. But I'm also I always talk a lot about negative results. So I would normally talk as decoherence and failures and stuff. But today I'm actually also going to talk about some constructive and positive results when I go to the next point on the agenda, being the scalable. So we'll have both some negative and some positive results. But I told you I'm going to zero in on an even more pretty dramatic limitation, which we call scale fragilities, where we definitely cannot allow distributed controllers to scale to a larger network. So here I'm going to soon explain exactly what the dynamics are, but basically we have a coordination going on in a network of, in this example, 34 nodes. Everything is stable and converges. But when we add the 35th node, let the agents obey the same protocol, we stability. So a true instability here. And we're going to see that this is a fairly straightforward algebraic property, but it does have some non-trivial consequences, and it lets us ask some interesting questions regarding topological properties of network systems. So that's what I'm going to go through in this first part of the talk. So it says already on the slide that we're considering consensus dynamics, and I want to argue that consensus dynamics are an interesting model class in themselves. It's kind of a prototypical distributed controller. It models, so physically it can be thought of as a mass spring system. And these springs being diffusive couplings that are prevalent in physical systems. So a power network or mass spring damper systems have these kind of these diffusive couplings where things spread in networks. And in many engineering applications, in particular multi-agent systems, the same type of relative feedback, so basically where the feedback is based on relative differences between agents, is key also in many engineering applications. So here, for example, this car is driving here, and a commercial adaptive cruise controller will measure the relative difference in velocity and position with respect to the vehicle ahead, whereas the absolute error, so this car's absolute position and velocity error with respect to some global reference frame is much harder to measure, but the relative measurement is readily available. So I kind of argue that consensus dynamics are interesting as a model class. And I'm sure many of you have encountered it, but just to go through what the dynamics would be. So first order, I'm going to talk about consensus of various orders. And if we look at first order consensus, often called information consensus, we simply have that each agent is a single integrator, and we have a control signal, which is just, as I said, a weighted sum of relative errors in the state. That could be the position. if we have a second order consensus, then you can think of every agent as having inertia or mass, even though not including that here. Then you have a double integrator, as every agent is a double integrator, and the control is now relative differences in positions and velocities. And this would be the model for formation control, so vehicle formations. We can generalize this to third order, to general nth order consensus, and I'm going to call it high order consensus if we have 3 or more integrators. So in this case, every agent is I'm showing you stuff with my arrow. I just realized you're probably not seeing that, but each agent is an nth order integrator. So you have n integrators, and you have a weighted sum of all the states, so positions, velocities, acceleration, and so on. What is important is that we're going to consider only relative feedback for reasons that I mentioned before. And third order consensus and higher is of course a theoretical generalization, but it also has some practical relevance. For example, if you have flying objects that are coordinating, you need to align in both position, velocity, and acceleration. So that's typically done. So we're going to consider this nth order consensus dynamic over networks that we can model as through graph Laplacian. So we consider network graph that has n nodes. And in general, the graph can be assumed to be directed and weighted. And then we have an important assumption that's going to hold throughout my talk, basically, is that each node is connected to at most q neighbors. Yes, I'm going to return to that assumption as well. Then we can formulate, we can write out the graph Laplacian matrix, which I'm sure you know of, and it's going to have eigenvalues, where the most important one would be the second smallest one, lambda 2, which, at least for undirected graphs, is called the algebraic connectivity. So I hope if I were in the room, I would see you nodding, hopefully, to see that you're following. Now I just have to assume that you are. Joel is nodding, that's nice. So I've said consensus a number of times, but I haven't said exactly what it means in this context. So basically, we're not stabilizing the network because we're doing a coordination. So consensus is said to be reached if all the states, if the agents agree on the state. So they are aligned in position, aligned in velocities. And of course, in general, we can have distances. So you don't need to be in the exact same place, but they should be with fixed distances between each other. At least in positions, and then the velocities should be aligned in accelerations and so on. But we don't care only that consensus is reached, but also that the consensus is reached also as the network scales and grows larger. And that is a property that I'm going to call scalable stability. And we say that a consensus design is scalably stable if the closed loop system reaches consensus for any finite network size, n. And that is how I want you to think of it, but it's mathematically a bit sloppy. So it is more correct to say that we have a family of graphs, Gn, in which the size n is increasing, and we want the controller U to drive a system defined over any of these graphs to a state of consensus. And in order to be able to say something about this, we're going to have to make some assumptions. That are important in order to be able to discuss scalability. And these are not very strong or restrictive assumptions, but they're important to keep in mind. So first, as I already mentioned, we're going to assume locality in the sense that every node only has a bounded number of neighbors. You can't keep getting more and more neighbors the network grows. If you came to the network and you started communicating with 5 other robots, you're not going to start communicating with more robots just because the network grew larger. And then the edge weights must be bounded. And other assumptions 1 and 2 mean that we have bounded degree graphs. And finally, and very importantly, we assume that the gains, AK, in the controller are going to be bounded and that they are fixed in the sense that they don't change as the network size grows. And under these assumptions, we can state the main result, namely that third and higher order consensus can never be stably scalable if the underlying network is such that the real part of the smallest non-zero eigenvalue of the graph Laplacian is decreasing towards 0 as the network size grows. So if you have this type of relative feedback controller of high order, you cannot allow it to scale. So what does this mean then? Well, it means that at some finite network size n, the system will inevitably be destabilized if this condition here holds. And we don't just get arbitrarily bad performance and instability at infinity, but at a finite n. And we're soon going to look at what type of graph families are affected. Oops, and that has, sorry, I'm jumping back and forth. And that has to do with the notion of locality or expansion. But I'm going to save that a little bit. I'm also not going to bother you with a proof. It is easy. You can find it in the paper that I quote there. It is based on Roth-Horowitz criteria. So basically, stuff that you learn in your undergraduate or possibly graduate controls course, but with complex valued polynomials. So those are conditions that you don't often see, but that exist, because we are considering directed graphs in general. But what this result means is basically that, as I said, at some point, the addition of a single node will cause instability. So this, what I simulated here, is a third order consensus. And of course, you again might tell me, okay, but third order integrators, third order consensus, sure, you showed us some UFOs, some flying stuff, but otherwise, is this really important? Maybe it is not so applicable, but we also actually have issues in second order consensus. So in fact, second order consensus will turn out to be scale fragile not in any type of graph, but in certain directed graphs. So here we have the condition that we can't have scalable stability if the network is such that the smallest non-zero eigenvalue moves towards the origin in a particular way, not along the real axis, but from the complex plane. That's basically what it says. And what type of graphs does this hold for? Well, in particular, the directed ring graph is one example, because here you can see what the lambda 2 looks like as a function of n. The real part goes to 0 faster than the imaginary part, and therefore follows that kind of trajectory. And in general, it is an open graph theoretical problem, even what type of directed graphs have complex valued eigenvalues, but there is some sort of cyclicity is required for this condition to hold. Something that moves around in a cycle. Here, so second order consensus, it has been shown, or if you model commercial adaptive cruise controllers in a simple way, you can say that they are to the first order is described by this second order consensus dynamics. And this would imply that a circular, if you're driving such cruise controllers in a circular formation, you're not going to have scalable stability. While if you drive them on a line, you're going to have scalable stability. On the other hand, you're going to have other performance issues like string instability and decoherence. But that's when we're talking about real stability, at least the string would be better. I also often say that tend to make the joke that if you want to go somewhere, it's better to drive on a line than in a circle. Yes. So we can sometimes it's fun to show some videos. Oh, now I also hear the videos, I realize. So here we have, of course, not a huge, okay. Oh, sorry. Did they both start going? We can simulate it on at least not simulate, we can implement these controllers on a network driving in a circle. And the stable formation doesn't look very like a lot of fun, at least stable. But the other ones are going to collide here, I think. So not great. I've been doing so much theory. I'm going to stop this now. So much theory throughout my PhD and and also after that, I've never had videos to show. But then we had this project where we implemented it, so I kind of wanted to include the videos. It's a little break for you guys who are listening. Okay. So go back to the high order consensus. I showed you. okay, we don't have scalable stability and in high order consensus under a condition on the graph families. But I didn't tell you what that means. And in second order consensus, I said that cyclic graphs are the issue, but I didn't tell you what the issue is really in high order consensus. And now that is what we want to do. So we have this condition that if the lambda 2, if the algebraic connectivity goes to 0 as the network size grows, then we can't have scalable stability in high order consensus. And
Emma,
for general,
can I ask you,
yes.
there is a question in the chat, and I think this is a good moment. Grant asks, so it says that typically first order consensus is common in applications, but can you give a sense of real world or real life applications for higher order consensus?
Yeah, so second order consensus again would be these formation controllers, and also in power networks, although you have absolute feedback in the frequency, it's more of a mass spring damper system. And high order consensus, yeah, that would be in particular flying robots would be one example where you would have to align in position, velocity, and acceleration. That is the model used for that. But otherwise, PI control. So if you want to do PI control of second order consensus, so you have a formation control, you have a cars driving around, or cars or robots doing second order consensus, but you want to eliminate stationary errors, and therefore you add an integrator on it as an integral controller. That would then again be a third order consensus. It looks a little bit different. That's why I'm not showing that formulation, but essentially it would be as an analogous formulation. So yeah, integral control, flying stuff, and otherwise the second order case would be power systems and basically coordination. Yeah.
Nice, thanks.
Yeah. So we're interested in undirected graphs where the algebraic connectivity goes towards 0. And for general directed graphs, it is hard to discuss this algebraic condition connected to the in connection to the topology, but I'm not going to go into detail of why that is. Some of you might be familiar, and otherwise we can discuss it after. But for now, let's see. We want to look at structure, and therefore undirected graphs are interesting. And basically, the condition that the algebraic connectivity goes towards 0 is linked to the topic of expansion, of graph expansion. And I'm not sure if you're familiar with graph expanders. I wasn't until, say, 5 years ago. But basically, asking whether or not a graph is expanding or not is analogous to asking whether or not there is a bottleneck in the graph. And I indicated that with the orange little balls here. So basically the question of whether you can separate two sets of nodes through two large sets of nodes by a small set of nodes. And that can be quantified combinatorically by this condition, the Tegling constant up in the upper right corner, which is denoted H of the graph. And it basically says you look through all possible sets of nodes and look at how many edges separate that set of nodes from the rest. And a fundamental result is basically that the algebraic connectivity is going to go to 0 if the Tegling constant also goes to 0 as the network grows. So basically, you need to have connections on the scale of the network. You can't have a large set of nodes X that are separated from the rest by a small boundary, is what the Tegling constant says. And another way to think of it, if one prefers algebra, we derive this condition basically. So if you can take the graph Laplacian and partition it in such a way that you get large blocks of zeros, so not partition it, but you can just renumber the vertices, move around the rows and columns. If you can do that so that you get big chunks of zeros in the corners, that is equivalent to having this type of this small Tegling constant. So you're going to have lambda 2 going to 0 if you have these large 0 blocks. And that is, again, equivalent to having a bottleneck set in the middle, which we here denote by x2. So that would be the general condition, but we also know a lot about the scaling of lambda 2 in certain families of graphs. So if we had lattices in d dimensions, would have this kind of scaling of lambda 2. Planar graphs, basically 1/n scaling. Constant genus graphs, that's a generalization of planar graphs. And then, of course, we have trees, also more or less a 1/diameter scaling. So the diameter will have to grow if you have degree bounds. So as I said, only expanders can have a non-decreasing algebraic connectivity while having bounded degrees, and that requires connection across the scale of the graph. So you can't have localized connections, and therefore they might not be useful for engineering applications where you always have this kind of physical limitations in communication. We cannot very well build a power network that looks like this graph in the picture here. That would weird wiring. But it's theoretically interesting to analyze this question. And of course, expander families, expander graphs, they are difficult. They're known to be difficult to construct, but you can simply do a regular random graph and they're going to be almost surely expanders. However, for the purpose of my application here, where I wanted to scale the network by simply adding nodes, I don't want to rewire the network as it grows, which I would have to do if I wanted to do random graph with degree bounds. Or I could do something like preferential attachment that's also known to produce expanding graphs, but that violates my degree bound. So a theoretical question that we have been looking at is what happens then if we have growing random graphs that are subject to degree bounds, and what are the properties of such graphs? And I can just point, if you're interested in such problems and bordering towards network science and graph theory, we just put up a paper on arXiv that could be interesting. But instead of going deeper into this problem now, I'm going to move on to some of another approach. So this would be a graphical approach to a network structural approach to circumvent the scale fragility issue. But there is another approach. You can do something else than just the typical consensus in order to achieve scalability, and that's what I'm going to talk about now. And this is something I actually haven't presented before because it's the work of my first PhD student, actually, Jonas. I realize I have a blurry picture. He just printed his thesis just the other day. It came out, and this picture is when in Lund we have the tradition that when you 3 weeks before your thesis, before you defend your thesis, you have to nail it to the wall, and you can see also a picture of all the other theses here in Lund. So that happened just a couple days ago. So this is Jonas's work that I'm going to present. And basically, the problem that Jonas's work addresses is two issues of scalability that occur in vehicle formations. And now vehicle formations and also high order consensus control. So this here would be the equation that I showed you before, relative feedback in positions and velocities. If we have a look ahead control, a directed graph, if the cars are driving in a circle, we know that we can't have scalable stability. That's a result I just showed you before. The system might converge for 10 agents, but when we grow it, it's going to be unstable. And even if you are stable, so if you're driving on a line, you're going to have performance issues. So something that is called string instability, and which means that you have error amplification along the string due to the bad control design, basically. That is, if you just look at the car ahead of you, you're going to have overshoots that propagate along the string. And here in this simulation, we can see an error that is growing as we have 100 agents. The error is 1,000 compared to 0.5 when we have 10 agents. So this is, of course, just a simulation, but it is a real performance problem. And Jonas's work, or our work on this topic, addresses both of these issues. So here, we're going to have to do something other than doing the nth order consensus protocol, because I already showed that suffers from these problems, basically. But we still want to have feedback that is relative and localized. So instead of the consensus protocol, consider now this more general operator AK, one one AK for each order, so one for position, one for velocity, one for acceleration, and so on. We needed to encode relative feedback only. We needed to have a uniformly bounded gain, so we can't increase gains as the network size grows. And we wanted to depend only on a localized neighborhood. And mathematically, those things are encoded in this by this class curly AQ of a adjacency graph W and a gain C. There's no need to. The points 1, 2, and 3 say what the maps say. Graph Laplacians, of course, as in conventional consensus, would be one example of operators A that satisfy these conditions. And the idea that we do here now is to, if we were to write the conventional consensus that I talked about until now, we write that in the Laplace domain, it would read here as in the first line. But what we ask now is, what if we instead could do? Was that a question or just Zoom Zoom sound?
I don't understand where this comes from because everybody's muted.
Yeah, no worries.
Not sure.
But yeah, so we are now in the Laplace domain, as I said. And what if we, instead of having these nth order integrator and so on up until the position error, instead could do a series of first order systems. That is the idea in serial consensus. So we kind of design the closed loop, and then we're going to look at the properties of the second system. I'm pointing here. You're not really seeing what I'm pointing, but there's not that many equations. So this serial consensus system, which is the one where we connect first order systems in series, is going to have some beneficial properties. We can show that it's going to maintain locality and sparsity. It's going to achieve scalable stability. It's going to have scalable performance and also certain robustness. So it's a simple idea and it's going to give us benefits. And I'm going to show you a little bit more how it works. So if we want to do, so now I apologize for the slides not being as pretty. I borrowed them from Jonas, but we're going to consider here now again, if we have n identical vehicles that are double integrators, then if we want to, the desired closed loop or the controller, the serial consensus will look like this here. I'm going to see if I can actually, no, I don't think I can annotate. The position feedback will be the two Laplacians added together, and the velocity feedback will be the sum of two Laplacians, and the position feedback is a product of two Laplacians, because that is what happened when you multiplied those two factors together. And if we write that out, we can see with the matrices, if we have a look ahead controller in a path, so cars driving behind each other looking ahead, the velocity feedback will simply be the looking ahead at the vehicle before, while the position feedback will be something that is no longer a graph Laplacian, but it's still banded. It still only has information from two neighbors, and it is still relative feedback. It's if you want to sum up the rows, they're all going to sum to 0, which is a condition for relative feedback. And what it does is you can implement this either by simply implementing this graph, the graph modeled by L squared, or you can signal. You can do a two-hop communication. So first, so one vehicle computes L1x being my difference with respect to the vehicle ahead, and then I send that to the neighbors encoded by L2. So in general, you're going to need either measurements from at most an n-hop neighborhood, n being the number of integrators, or you simply do message passing. So you're going to have to message pass n-1 times in order to implement this. So that is a cost of doing serial consensus. The benefit being that you have scalable stability. Proving stability here is actually almost trivial. I'm sorry that it looks blurry. I didn't know that would happen. But if you can write you can write the serial consensus on state space form as here below with the state psi, and you can see immediately, since it is upper the block triangular, that the eigenvalues of the system is going to be given simply by the eigenvalues of the Laplacian. So just as first order consensus is easy to analyze, this one is going to be super easy. So as long as the graphs are connected and the Laplacians have nice eigenvalues, the serial consensus will too. So apart from scalable stability, we're also going to have strong transient performance guarantees, and that is maybe the best argument for doing this. So in order to talk about performance, we should discuss the spacing errors. So in a platoon, it is natural to consider the difference with respect to the vehicle ahead, the distance, and how that relates to the DI, which is the desired distance. And in general, of course, you can consider the relative errors with some Laplacian L that encodes these what the distances are that you measure. And it's also natural to consider absolute velocity errors. So how much too fast or too slow are you driving? And then, of course, the most natural signal to bound in a vehicle formation is actually how large the absolute deviation is in terms of this error. So so this supremum over t for the infinity norm of the position error, that if that is large, you actually run into the car ahead of you. You're going to collide or not. I'm saying it's the most natural signal to bound. In the string stability literature, where they analyze this situation where errors propagate, this thing which you're actually typically after tends to be hard to capture and describe, but we succeed in doing it here in this case. You tend to instead look at norms, which would, rather than this point that I have drawn a little star, that is the actual peak of the transient, the string stability literature might look at various signal norms that instead might capture the area under the curve or various intervals. But what we can say here is that if we're interested in this actual deviation, and we can say that scalable performance is attained by a controller that can make sure that this error remains bounded as the network size grows. And they remain bounded in terms of the initial error. And we can prove that. So this is a theorem. What does it say? Well, it says that the serial consensus controller for the second order case, so being the platoon, the vehicle formation problem, then we have this scalable performance guarantee, and we have an expression for what alpha is. And this, of course, is in the case of uniform, that every agent has the same gains. I think it is pretty robust to having heterogeneous gains, but it's harder to prove. I'm looking at the time. I'm going to go through. I don't have that much left. I think the proof here is based on writing up an alternative state space realization, and then you can look at the infinity norm of the state. And do a clever bound here, where you get, we have a side result that is an interesting linear algebraical thing, where we have this condition number of the diagonalizing matrix that enters is going to determine the factor alpha. The fact that term that is then written as being smaller than one, that's smaller than one, is the fact that it's just a simple first order consensus. It's just a Laplacian. It's known to be contracting. It can't do anything else. And then we know that we have these guarantees on the transient, which again you cannot have in conventional consensus, because then you get these kind of second order oscillatory behaviors that are not contracting in the same way. So it's very, very useful. We know that these performance guarantees hold also for higher order systems, and which makes it useful for PI control. Again, that is one of the answers to why would higher order systems be interesting. Distributed PI control can be tricky. I worked a bit on that in my PhD thesis. And serial consensus here for implementing that, again, at the cost of some more communication hubs, offers a new structure, a new way to do that. The benefits would be, I'm going to simply show some plots. So what do we see here? We see a second order serial consensus where under a low disturbance, so there is some constant disturbance acting on all the cars. If you would just do second order consensus, you would have some stationary error that causes an absolute deviation that does not decrease in time. But if you do the third order serial consensus that implements PI control with a particular choice of states, you can see the error, the relative error decreasing towards zero. So you eliminate stationary errors, and you actually also have a very nice and bounded transient. I am going to start rounding off soon. I just want to say that we can also show. Yeah. So one thought. The first thing that struck me. So okay. So why does this work? How can we say such strong things? Okay, this works only because of the very particular structure. You're picking. I'm trying to find a way to show it. You're picking your operators to be products of Laplacians, and what happens if you then deviate from that particular structure. So maybe here is a good way to show it. If the closed loop is you need the particular square of the Laplacian, and then Laplacian cube and so on. Does that still work if you have non-ideal conditions, or is it very sensitive to having this particular formulation? Truth is, no. As long as you have this idea of putting first order systems in series, you're going to have the benefit. So we show robust stability under certain model errors, additive and multiplicative, and we can also generalize this to where the operators are not just linear Laplacian matrices, but rather the operators curly n that are like Laplacian operators that might be subject to delays or saturations and so on. If they are sufficiently smooth and differentiable, you can do this compositional consensus, which generalizes the serial consensus. And we're just submitting a paper to show that this works very well. Again, just a simulation here to show where A would be this what this is a simulation. It's a little bit of a contrived example, but you imagine, I think we have time varying connections, so the connection strengths vary sinusoidally, and with compositional consensus you can achieve second order consensus stably, but if you have a conventional second order consensus where the connection strengths vary like that, you're going to be unstable. And then the naive serial consensus is the difference between those two. It's a little bit hard to explain. You also have stability, but you have slightly worse performance. But this is to say that we can have non-ideal conditions. We can allow doing this idea of composing the first order systems, implementing that by having this additional communication hub offers a lot of advantages compared to the conventional protocols. Robust performance, however, is a little bit difficult to guarantee, because in any network application, you can construct really bad examples, really unfavorable disturbances that can, or perturbations that can lead to a bad performance. For example, you could imagine a worst case disturbance that perturbs every vehicle in a very particular way, that pushes along the string, and then you would run into issues. It's hard to guarantee to do robust performance guarantees without assumptions on the disturbances, but of course it's subject of ongoing work. But robust stability is done basically, and this is, if you're interested, you should look at Jonas's thesis. So again, a takeaway of the second part of the talk would be again, that serial consensus can achieve scalable stability and performance, while conventional consensus in second order would have these unfavorable transients, and in worst case scale fragility. We can do this and have firm guarantees on the transient performance at the cost of an extra communication step. It is not true that you always need an extra communication step. If you're driving in a platoon, you can have look ahead control in velocities, I think, and look ahead and look behind in position. And that, if one works out the examples, what the Laplacian squared means is going to be a look ahead and look behind structure. That structure is known, was already observed in the Platonian literature to be beneficial, but no one really, they didn't have a good explanation for it. But here in the serial consensus, it can kind of offers an explanation to why that works, because then we can factor it out to get these two terms. No one, it doesn't seem to have been observed in this literature before. It was more of this curiosity, like, yeah, mix look ahead, look behind control, and that's going to work. But here we now have an explanation. So I'm going to conclude. What I started talking about was this little bit curious problem of scale fragility, where localized high order consensus does not scale stably to large networks. And a structural solution or a structural way to address this would be to study expander graphs, because the problem does not arise there. But there are other issues with considering that structural solution. Instead, we looked into a control architectural solution, which would be the serial consensus that emulates first order systems connected in series, which gives you strong performance guarantees. Some ongoing work and collaboration opportunities, throwing it out there. Of course, we're thinking of implementing the serial consensus. I have some robots. If anyone out there wants to implement it on more robots, that would be beautiful. Looking into other application areas, energy systems, not just this particular issue, but also other performance issues. That issue of coherence and so on is things that we're interested in. I am also interested in graph theoretical problems. As I said, we are studying these growing graphs under degree bounds. This turns out to be a pretty fundamental graph theoretical network scientific problem that we're working on. And then, of course, I showed you one slide in the beginning of other problems that we're considering. I am in general interested in control and learning under structural constraints. So whenever the signals that controllers and observers obtain are limited by a network structure, you're going to have difficulties, and that's what I'm interested in. So with that, I would like to thank you and see if we have any questions.
Thanks so much, Emma, for the great talk. And it didn't look at all like you said that it was generated very recently. It was very, very good. So let's open the stage for questions. You can either write in the chat or raise your hand and directly ask. I maybe will start with an icebreaker. I really like the final part on the compositional properties, which is very interesting. I wonder in this context, is it more of a, because you could interpret this result, the power of these results in two ways. One is I have already given a bunch of systems. I can analyze consensus for these systems, and now we have a property that tells me when I compose them, I have something preserved, which is nice. Yeah. But on the other end, it would be the other way around. It would be even cooler, because now you're given a huge mess that you cannot really understand. And now you can design some techniques to decompose it in a way that the single pieces can be analyzed for consensus, right? So which of the two directions is this?
I would say,
yeah.
So there is a tradition, of course. It's a common problem it's a general problem in automatic control, of course, methods by which to do modular design. So you have passivity guarantee, the passivity theorems. We have port Hamiltonians, of course, they are passive anyway. And you have small gain theorems, and everyone looks at this. Okay, so how can you compose problems? And of course, the tradition in distributed control would be to connect. So every agent has a passivity property, and then the agents are connected together. What we're doing here is, of course, we're looking at the systems would be the layers in a higher order integrator system. So every single one of these composed system is already a network. But the benefit is that we can, there are like millions of consensus publications out there, and I don't even think I'm exaggerating. And they're looking at second order consensus, because first order is simple enough. And then there are all these papers that look at second and even higher order consensus under time delays and under time varying connections. And I mean, there's a lot of literature studying the conventional protocol, where they have it up here, which be on top row, under such non-ideal conditions. And what we say is, okay, it suffices to take all the 500,000 papers that treat first order consensus under non-ideal conditions, and then we know that we can guarantee high order consensus to be working. So I think that is the argument we want to make. We're not going to sit down and look at various curly L's to see if they can reach consensus, but we take any curly L that has been shown to work in literature can work for high order systems.
I see. I'm curious if there is also other, well, yeah, I'm sure this is in the future work, but this is kind of a series composition or sequential. I'm curious if the algebra of compositions can work more broadly, right? For sure, you can. I don't know what the meaning is of putting these things in parallel, but probably that will work as well.
Yeah, that's possibly true. Exactly. The conventional consensus cannot be interpreted as parallel. Really, it's something else. It's just one system, but. Yeah, maybe there are other compositions that could work. I think you need to maintain the in
I'm
this
biased.
application.
Every time I see compositions, I imagine many more ways.
Yeah.
So
yeah, I think, and then I think there's a subtle difference in this plot between A and C. So C being just taking the structure of the conventional of the serial consensus for the linear case and having the nonlinear operators, whereas the compositional consensus is doing something slightly different, and it's better. So here there are subtle differences in the way you compose the functions. Both are implementable. Both only require 2 hops, but the way they derive the signals is a little bit different.
I see.
Yeah.
Okay, thanks so much.
But yeah, this is really hot off the press. So
yeah, no, definitely. I'll have a look at that. I'm curious. Any other question for Emma? Yes, Eugene has a question. Okay. Eugene is a PhD student in my group, and he's been infected by the compositional virus as well. So
okay, great. So yes. I showed this on half a slide in the end. I'm sorry. I should have shown more.
Yeah, you triggered us. Us.
That's good. Hi, Eugene.
Sure. So, hello. Yes. First, it's a nice talk, and the question I want to ask is, the most general topic in this kind of consensus control or network control is that we can design control techniques and control algorithms for the agents, like distributed ones. But what I'm wondering is there a way of designing the architecture or at the same time, like for instance, for plateau control, can we also co-design the hardware infrastructure to enable more connections at least temporarily, or design the time varying connection map between vehicles to make the strategy more efficient or enable better control strategies?
This is a very good question, and I think that is maybe where the tradition has been. So if I'm going to flip through some slides again. So I can do it on hand of this image. So of course we can write out this vehicle formation control, this U signal that I have here with the relative differences, and then of course a typical question is, okay, so what if I just look at more neighbors? We know that we have the string instability problem. What if I look at more neighbors? I look and one thing you can do is look ahead and look behind as well. That will solve the string instability problem, for example. And then you can look at more neighbors. You're going to be more robust if you add more neighbors. However, some of the performance issues are not going to be alleviated. They're just going to be, you don't have a fundamental performance improvement. You just have a factor of improvement. And then, of course, you can imagine these connections being time varying and so on. And that is things that people have looked at. What we argue here is that we can, if you have access to more neighbors measurements, then it's much more efficient to do this, to do the serial consensus. Then you're going to have actually a fundamental performance improvement rather than just increasing the neighborhood size. On the other hand, then so and we can show with this compositional argument that even if these additional measurements are subject to time delays, even arbitrary time delays, as long as they're bounded, the time delays, or if they are intermittent, so sinusoidally varying, we can try such things, and it's still going to give us benefits. Possibly, as I said, performance guarantees are hard to show because you can design really mean delays and things, of course. So it's hard to guarantee performance under some very mean disturbances. But as long as they are nice, I think we future work is going to be to show performance guarantees. But it's a good question. The co-design of network structure. Yes, I'm interested, as long as I try to limit the problem to not needing to design things subject to a scaling of the network. So I don't want to have to redesign just because more cars came along. I don't want a car number 2 to need to know the fact that we are now 100 cars rather than 10. If you see my point.
Okay. Yes, I see. I see. Thank you.
Thanks so much, Eugene, for the question. Any other question? Doesn't look so. But I guess in your last slide, you had your link to the website or something. If people want to reach out, I think.
Yeah, it's tegling.se, actually. Just
perfect.
Feel free. I had my email address there as well. So yeah, you feel free to reach out. And I think I'll probably I'll be at ACC as well.
Oh yes, I'll be there as well.
American Control Conference. So
yeah,
I suppose I'll see some of you there.
Yeah. Amazing. Thanks so much, Emma, for the great talk. It looks like you just opened a lot of new things to do with these results.
I'm very grateful. Yeah, I chose to present these. I like to talk about these because they're pretty. It's just simple algebra, and people tend to understand it. It's easy enough for a late Tuesday afternoon. Although for you it's just Tuesday lunch. But
actually, I'm in Switzerland right now, so I share your time experience.
Okay.
Yeah. Thanks so much again for the great talk, and wish you all the best. And see you soon.
You too. Thank you so much for having me. Bye-bye.
Bye-bye.